Welcome back, everybody. This is Mr. Wakefield. We're continuing on with the second half of the 3.3 worksheet. Please join me at number 7 right here of that 3.3 worksheet. And it talks about now going backwards now, where you're giving the zeros in advance instead of having to find them. And then you have to find the f of x that they came from. And so instead of starting out with the f of x, we're now going to finish with that. And the way to do this usually is you take this thing that's on the front side of the 3.3 worksheet, this thing right here. What this is saying is that any polynomial, if you break it all the way down to all of its linear factors, and sometimes we don't take it that far, but if you did, the point is that if you take all your zeros for your function, it can be broken down like this. And this includes the possibility of some of them having a multiplicity. Like, for example, that problem where we had a multiplicity of 3, you'd have to have 3 of those in here amongst all of these. So, like, for example, see how it says degree n? If your degree was 5, then you'd have to have 5 of these brackets. But but 3 of them would have to be the x plus 1, x plus 1, x plus 1. If it was one of those problems like we saw earlier, where the x plus 1 was supposed to appear 3 times. Remember this one right here? That would be 3 out of the 5 that you would have. However, in this particular problem that we're doing right now, that we're about ready to do, because of the fact it says that the degree is 3, you're going to have 3 of these brackets. You're also going to have this constant. This is a constant number right here. I want to make that clear. There's no variable there. Although you could have a variable there in other problems in the front, but and we'll see that coming up, but not here. So here's how it works. All right, since this problem says that it's degree 3, like I said, we're going to have 3 brackets. And how it works is like this. As we talked about, let me put the A there. And then you put your 3 brackets. Okay, and just like it says, all right, you got the A, and then you got the brackets for each one, from the first 0 all the way up to the nth 0. So if n is 3, then like I said, it'd just be 3 brackets. And so here we go. So it's going to be x, and then you say x minus all of these. So it'd be x minus 2, x minus negative 3, which is the same thing as x plus 3. All right, on the double negative right there, and then x minus 5. All right, but the problem, though, here is, what is A? All right, well, the A depends on this final condition here, where they actually say they give you a function value that matches up with the x that gets plugged into it. When they give you that condition, what they want you to do is this. They want you to plug the 6 into the f of x, because the f of 3 is equal to 6. In fact, let me write this down over here. F of 3 is equal to 6, right? And so, because f of 3 is what happens when you plug in 3, on the other side of the equal sign, we're going to have a times 3 minus 2, 3 plus 3, and 3 minus 5, because you put the 3 wherever the x was. And so you take this equation right here, this right here, you take that and you solve that equation. Get A by itself, in other words, because that's the only letter that's left there. You get it by itself. How do we do that? And that'll tell us what A is equal to, though. We do that by, first of all, figuring out what these brackets are equal to. And then go ahead and multiply all this together right here. A times 1 is A. Times 6 would be 6A. And then times negative 2 would be negative 12a. All right, so we get 6 equal to negative 12a. We then divide by negative 12 to get the a by itself, and we get a is equal to negative 1/2. All right, now that we know that the a is negative 1/2, we plug it back into this original function here, And we pretty much have an equation here that satisfies all the conditions. All right. By the way, isn't it clear that those 3 zeros actually have to be 3 zeros here? Isn't it clear like I satisfy that condition? Because if I plug in 2 into this one, sorry, that fell out. Let me zoom out here. If I plug 2 into this one right here, that makes the whole thing 0, and that's what a 0 does. If I plug -3 into the second bracket, it makes this bracket equal to 0, which would then make this whole thing equal to 0, because this is one of the factors. All right, we have a total of 4 factors here. The -1/2 is being multiplied by each of the 3 brackets. That's a total of 4 factors when you have 3 brackets and a term in front of the first bracket, and all of those things are being multiplied together. And that's all you have is just the term in the brackets. That's a bunch of factors is what you got there. And so if any of them are equal to 0, it's going to make the whole thing equal to 0. Okay, so the 5 makes the last bracket equal to 0. So I'm just explaining that it all makes sense that this thing that we have right here satisfies all these conditions as the directions say they're supposed to. Okay, so we pretty much got it, but the problem is that they want us to write it in polynomial form, which means that they don't want any brackets. They just want a bunch of terms being added and subtracted together. So we got a little bit of work to do. What I'd like to do, anytime you have 4 things being multiplied together like this, in order to figure out what it's all equal to, in order to get rid of the parentheses, is to multiply 2 at a time. So I'll go ahead and multiply these 2 first. It's easier to do the single term last, in my opinion. If I multiply this out and combine like terms here, the -5x and the +3x, I'll just combine those together right now so I don't have to write down so much stuff here. I get this right here. Okay, that's just from those two. Those 2 brackets become this. And then I need to multiply that by the x minus 2. I get, let's see, x to the third. I'm going to distribute the x through the second bracket. Distributing the x through the second bracket, I get x to the third minus 2x squared minus 15x. And then I distribute the negative through, so the -2 through the same bracket right there. And I get negative 2x squared plus 4x plus 30. And so then that is the... Actually, I want to combine like terms on that. You're welcome to do that. Just don't combine terms from one bracket to another. You can't, because that would mean that you're adding and subtracting. You're not supposed to add and subtract terms from one bracket to another. But because this is the answer you get when you multiply these 2 brackets together, all right, and since you're supposed to put this in brackets, I'll go ahead and put that there. Because we still have to multiply by something and it's got more than one term, that then makes this whole thing go into one single bracket. And you're allowed to combine like terms inside of a bracket as long as there's no smaller brackets in there to get in your way. If it's just a polynomial, you can do that. So before I multiply by -1/2, if you like, you can combine like terms right here. Here we go. All right, there we go. And then 30. And so if I then finally distribute out the -1/2, my final answer is going to be f of x equal to -1/2 x to the third. I'm distributing the -1/2 through all four of these terms, plus 2 x squared, and I say that because -1/2 times -4 is equal to a positive 4/2, which reduces down to 2. -1/2 times -11, and negative times negative is positive. 11 times 1/2, if you multiply those together, you get 11/2. It's just like multiplying a fraction times a term. You make the 11 into a fraction, you multiply the fractions together. All right, -1/2 times positive 30. Negative times positive is negative, and that would be 30/2. Okay, 30 over 1 times 1 over 2 is 30/2, but that reduces down to -15. I forgot the x right here. Sorry about that. I forgot the x in behind the 11/2 right there. Okay, so get that in there as well. But that is Problem number 7 right there. All right, so one additional note here, because you'll see this in your homework. If they said that, for example, let's say that they said that you had zeros of 2, but let's say that they said that the 2 had multiplicity of 2 or something like that. Okay, so here are some examples of some possible homework problems you have here. For example, number 55, notice it gives you, again, 3 zeros. It says do a degree 3 right here. So it's a very similar problem. It has the condition there. Just wanted to point out that when your zero, with one of your zeros actually is the number 0, that would mean x minus 0 would be one of your brackets. But think about it, you guys. X minus 0. If x minus 0 is a bracket, isn't x minus 0 just the same thing as x without the bracket? And you don't need the bracket when it's just a single term. That's why I say without the bracket. So x minus 0 is the same thing as just having x without the bracket. So, although you could keep the x minus 0 like that if you want. You could do that. So, what you would do, though, if you wanted to, is you could just change this to x and then combine the x with the a. You could write ax, and then you could write x plus 2, x minus 1, for example. All right, x plus 2 for that one, x minus 1 for that one. Again, you got to change those signs when it goes inside the bracket. All right, so that would be number 55. You still got to figure out what the a is equal to and get rid of the parentheses and all that. By the way, one other thing, and we saw this earlier, if it says that it has a multiplicity 3, that means what? That means that x plus 3 is going to appear 3 times because it has multiplicity 3. So it's going to say x plus 3, x plus 3, x plus 3 with the a in front of it as well. Okay. If this had been multiplicity 2, then you would say x plus 3 just a couple of times. All right, so just wanted to make sure that that kind of stuff was clear there. All right, in fact, here's a good example then here in 59. It says that 1 has multiplicity 2. That means that you'll have a couple of x minus 1 brackets, not just one, but a couple of x minus 1 brackets in that particular problem. So just wanted to make sure we understood some of those other details before we move on. This next problem here is very similar to number 7. It's just a much more complicated version of it because of the i's and the multiple terms and stuff. I'm going to go ahead and skip that since it is so similar, though. You can write skip right there. You're not going to be tested on that particular problem exactly because of the fact I'm skipping it. And obviously, you do need to be responsible for knowing all the other problems in this section, like everything else on the worksheet packet, but you don't need to worry about that one. All right, now as we flip over to the final part of 3.3, finally, what a long section. All right, we got 4 more problems here. And once again, it says find the zeros, just like we did in problems 4, 5, and 6. But the difference here with these problems is that they do not start us off with a 0. They don't give us a clue on what to start off with. Remember, in problems 4, 5, and 6, all right, they started us off. They started us off with 2 minus I here. They started off with 1 right here in problem number 5 and I down here in number 6. They don't do that this time, okay? So let's look back in when we do these 0 problems, all right? Again, we still set the f of x equal to 0, and we still do the GCF if possible. But then when we get down to this step, you guys, take a look. It says we try to do synthetic division, but we got to have something to put on the outside of the synthetic bar to start us off, okay? You got to have that number out there, otherwise you don't know what to do. So it says right here, if the problem doesn't give you a 0 to try, well, in all the problems we've done so far, it has given me a 0 to try. So I've always been able to start off with something. This time in these last 4 problems, I don't have that, all right? So if it doesn't give you a 0 to try, it says first use the conjugate zeros theorem. Okay, now let's back up. what does that mean? It means that if, and you realistically can only use the conjugate zeros theorem if it starts you off with because you're not going to have a complex number. That's when you use this conjugate zeros theorem, is when you have an imaginary number, all right, with the I in it. And you already know that 2 minus I is a 0. That automatically tells you that 2 plus I is a 0. But the problem is that if they don't already tell you that you have a imaginary number that is a 0, then you don't have anything to build off of with that theorem. That theorem is dependent upon you already knowing what one of the imaginary numbers is going to be as far as being a 0. Okay, so if they don't tell you that some imaginary number out there is a 0, you can't use the conjugate zeros theorem in order to come up with another 0. Okay, so only when they give you a imaginary number and they say that it's a 0, do you do the conjugate zeros theorem by then saying that the other thing here, 2 plus I, is also going to be a 0, and then you can use that. You'll see here in these last 4 problems that they don't give us any clues about anything, imaginary numbers or otherwise. And so the conjugate zeros theorem is not going to work for us in these problems either. So as a last option, if they don't give you a 0 to try, and you can't do the conjugate zeros theorem, then the only other thing that we can really rely on, unless we want to start guessing, and that is definitely not recommended, because you could be sitting there forever trying to find a number that actually works when you do the synthetic division. Okay, remember, you need a remainder of 0 in order to be able to factor it, okay, and you need to be able to factor it somewhat in order to get to figure out what those zeros are. So, you could be sitting there all day trying to figure out the number that goes out here that gives you a 0 remainder. Don't want that, right? So, this last option is something called rational zeros theorem, all right? And I promise you guys that if you got a problem where it doesn't give you a 0 to try, and you can't do the conjugate zeros theorem, the rational zeros theorem will at least get you to a point where you'll be able to break the problem down to either linear and or quadratic factors. And as we said earlier, once you get down to that point, you should be able to normally set those equal to 0. Okay, we had that one exception where you had the quadratic factor with the i's in it, but other than that, you can set each factor equal to 0 and then find all of your zeros that way. Okay, so the rational zeros theorem in this case is going to help us get down to the linear and quadratic factors. Let me explain what the rational zeros theorem is. Here's how it works. You take the coefficient of the term that does not have a variable in it. Okay, let's put that over here. All right. And then you take the coefficient of the highest degree term, which is 1. All right. And here's what you do. You have to take all possible combinations, positive or negative, that are factors of 12 and factors of 1. And I put the bar there, that fraction bar there, for a reason. It's because you have to take fractions that are combinations of. Let me show you what I mean. Let me list out the factors first. What are the factors of 12? They are 1 and 12. I'm separating this for a reason here. You'll see why. 2 and 6. And then 3 and 4. I separated a little bit too much, but that's okay. Then... same thing on the bottom. The only factors of 1 are just 1. Okay, that 1 is the only factor of 1. You also need to consider, though, positive and negative of each one of these numbers that we have. So plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, and plus and minus 12. Now, and also plus and minus 1 down here. You got to take all different possible combinations of the numbers on the top being divided by the numbers on the bottom. However, if the bottom is just equal to 1, plus or minus 1, then the top ends up being all your different possible combinations. Okay, because when you divide by 1, that doesn't change anything, does it? And if you divide by -1, because we've already considered both positives and negatives on the top, that's not going to matter in this case either. So there's a total of 12 different numbers here, you guys. Okay, 6 numbers, but then a pair for each one for positive, one for negative. I guarantee you that if you keep on doing synthetic division on this thing until you get it down to linear and quadratic factors, all right, you can find the numbers that have to go on the outside of the synthetic bar. You can find all the numbers you need in this list. It's not going to be outside of that list, okay, in order to get down to the linear and quadratic factors. I'm not talking about what happens once you get there. That's different. Then you can't necessarily rely on this, but this will get you to the linear and the quadratic factors, and then we'll go from there. So you might be wondering, well, gee, how do I know which one to try first? I usually try to do the easiest ones first, all right? In the interest of time, though, I'm just going to go ahead, since I've done this problem before, I'm going to go ahead and tell you right now that 2 is one of the numbers that works. And so, but yeah, if it doesn't work, you guys, and what do I mean by it doesn't work? It means that if your remainder, your last number on the bottom of the synthetic division on the right, if that number is not 0, that means it didn't work. It has to be 0. The 2 right here is going to give me a 0 on the bottom right-hand corner where the remainder goes. That's what you want, all right? That's what you need. Let me go ahead and do the synthetic division right here. And sure enough, you can see that it gives me 0. If you had done 1, for example, or -1, for example, this number would not have been 0, and then you wouldn't have been able to use that. Okay, you got to have that 0 in order to factor this. So what does this become? The f of x becomes, and by the way, again, we're going to set that equal to what? Since we're trying to find the zeros, we're going to set that equal to 0. And then we're going to solve that equation, but the non-zero side of the equation is going to become what? It's going to become x minus 2. Remember we said the first bracket, you change the sign of that number there, combine it with the x, and then these numbers right here tell me what the other bracket is. X squared minus, or pardon me, plus x minus 6. And as I promised you, all right, the rational zeros theorem over here will get you to having a linear and a quadratic factor. It will get you there. Now that you are there, what do? Excuse me. What you do, like we did before, is, since we're trying to find the zeros, is we just simply set each one of these factors equal to 0 right here. X minus 2 equal to 0. Or x squared plus x minus 6 equal to 0. Okay. And then we solve those. Since the first one's linear, you just move the 2 over. Since this one is quadratic, though, I need to factor the non-zero side of the equation. We end up getting, if you do the Berry method, we end up getting plus 3 and minus 2 on that. And as you guys know, once you do the factoring in a quadratic equation, you need to set each one of these factors equal to 0 and solve those equations. We get what? We get -3 or 2. Okay. Okay, so you only have 2 different answers right there, but we have 3 answers total in reality. Okay, notice how it says list multiple zeros as necessary. What they meant by that was, if the same zero, if that same number appears more than once, normally you don't have to list that out. Okay, normally if the same number appears twice when you find a bunch of solutions, you can just list out all the different ones. Normally they just want you to say all the different ones, but in this case, they want you to, if it pops up more than one time right here, they want you to list it both times. All right, the point that they're trying to make right there is that if you do list out those things multiple times, if they pop up multiple times, what you're always going to get, you guys, is you're always going to get, if you have a degree 3 polynomial, you will always get 3 answers. If you have a degree 4 polynomial, you'll always get 4 answers. All right. A degree 5 polynomial, like we have in number 11, will always get 5 answers. That will always happen if you account for a couple of things. Number one, you count when something pops up more than once. And number two, you account for the fact that if you have imaginary numbers, okay, you don't neglect those either. In some previous math problems, in some previous math classes, those imaginary numbers sometimes were neglected, all right, and we threw those out, but not here. Okay, as we've seen here, we're definitely acknowledging imaginary numbers in this section. So if you get the square root of a negative number, you can't just say, oh no, that's not an answer here when we're doing these problems. In fact, I know that because see how the directions say they want you to include imaginary numbers in your answer here if you get, say, for example, the square root of a negative number. Or if you get I in your answer, all right? You can't just say, oh, that's not a real answer. No, you got to include that, all right? Just like we've been doing, all right, in some of the previous problems that we've already seen in this big 3.3 section, all right? Okay, so here in number 10, again, we follow our process, our normal process when we need to find the zeros. We set the thing equal to 0. All right. We find the GCF. Oh, wait, hold on just a second here, you guys. The GCF is what here? All right. The GCF is actually going to be not equal to 1 this time. All right. You got to factor that out right here. Okay, otherwise the rational zeros theorem really is not going to work because theoretically the top part of the rational zeros theorem is supposed to be that term that does not have a variable in it. Well, there is no term here for that, which means that this top part would be 0, and that's not going to get you anywhere. So you really, not only are you supposed to factor out the GCF, but you really are going to be stuck if you don't here. So factoring out the GCF, which actually ends up being x, I get 3x to the third minus 9x squared minus 31x plus 5. Okay? And then what you do when you factor out the GCF is you just do the same thing with the leftover polynomial right there that you would have if the leftover part here was the original problem. You do the rational zeros theorem on that because, again, they don't give us any zeros to try, and we can't do the conjugate zeros theorem because there's not an imaginary number to use for that, like we talked about a few minutes ago. So you take the 5 and the 3, the coefficient of the term that doesn't have any variable in it, and you take the coefficient of the highest degree term 3, and we say this right here, factors of 5 divided by factors of 3, okay? And so what are the factors of 5? It's just 1 and 5, right? What are the factors of 3? It's just 1 and 3. But remember, you got to consider both positive and negative for all 4 of these numbers. So how does this come out? It's a little bit different than the last problem because we're not dividing by plus or minus 1 this time. We're dividing by plus or minus 1 and also plus or minus 3. So it creates a whole different set of possibilities. Watch what I do here. I'm going to take every single different possible combination. Plus or minus 1 divided by plus or minus 1. What is that? That's plus or minus 1 because 1 divided by 1 is 1. And then how about plus or minus 5 divided by plus or minus 1? That is going to be plus or minus 5. How about plus or minus 1 divided by plus or minus 3? Okay, plus or minus 1/3. And finally, plus or minus 5 divided by plus or minus 3. Okay. Plus or minus 5/3. So again, we have 8 possibilities here. Okay, usually I'm pretty nice about not making it fractions or really big numbers or something like that. Usually you can find a number here that's not too big. It's not a fraction. I'm not saying there won't be any fractions in the final answer when you find your zeros, but you can at least get down to the linear and quadratic factors by just using relatively small numbers without in them being fractions or something like that. Not saying that the homework, I'd have to go look again, but not saying that the homework is necessarily that way, okay? But on the tests, I'll be nice like that, and also we'll be nice right here in these problems. So, again, could try plus or minus 1. I promise you already, those don't work. So just in the interest of saving time here, what does work is the positive 5 right there. Let's see how. Again, since I've already factored out the GCF, you guys, you are just building off of, like usual, once you've already factored something out. And please remember, you guys, the x is the same thing as x minus 0. So that is a linear factor. And linear factors, you guys, linear factors, they are... we don't touch those, all right? Those, that's what we want. We want linear factors for the end of the problem when we set every factor equal to 0. Right? That's definitely a good thing, all right? Linear or quadratic. So leave that x alone and just factor whatever's left over that's not linear or quadratic, all right? Until we do have nothing but linear or quadratic left, all right? So since this is degree 3, that's not quadratic yet. So I got to take that, and I'm going to use my numbers from the rational zeros theorem to try to find something that will break that down for me. All right, I promise you, though, because of the rational zeros theorem, all right, that will, one of these 8 numbers will get this factor broken down until you've got linear and quadratic factors. All right. Won't necessarily, like I said a few minutes ago, won't necessarily take you any further than that, these 8 numbers, but it will get you down to the linear and quadratic factors. One of those 8. All right. So I'm just doing the normal thing right here with the synthetic division. And as you can see there, that ends up being 0. Okay, now, what does this mean? This means that... I now have what? I now have x, and then the this polynomial right here breaks down to 2 parts, like always. Okay, the smaller bracket, and then what's usually the bigger bracket there. The smaller bracket is x minus 5, changing the sign of the 5 there, and then this is 3x squared plus 6x minus 1. 3x squared plus 6x minus 1. And so we now have what? We now have nothing but linear and quadratic factors. All right. Again, x is the same thing as x minus 0. It's a linear one. X minus 5 is a linear one. This is a quadratic one because of the x squared. So what we normally would do at this point is we set each one of these things equal to 0, just like we did in the last problem. And unfortunately, although we can overcome it, unfortunately, that quadratic factor, we're going to have to do the quadratic formula, and that's just a little bit more of a pain, isn't it? All right, to have to do that. So I got x equal to 0. X is already by itself. This one is x equal to 5 when I get x by itself. But I still need to what? I still need to do the quadratic formula on this because this does not factor. So I get x is equal to negative 6. By the way, the 2 answers that you get from this equation right here are not on this list. That's why I kept on saying, okay, that you can't rely on this necessarily once you get to linear and quadratic factors, but it will get you there. Okay, if you can't, if they don't give you a root to try or a 0 to try, like I said, and if you can't do the conjugate zeros theorem, I promise you that these ones here will get you to the linear and quadratic factors. And then you set them equal to 0 and all that stuff. All right, so let's see what this ends up being. I just want to remind you of that, though. Okay, so here it is. What does this become? This ends up becoming the inside of the radical is equal to, zoom in there a little bit more for you. The inside of the radical is 36 plus 12. 36 plus 12, which is 48. Okay. And that simplifies down to be, if you simplify that radical, you can factor out a 16. As we reviewed in the prerequisite review packet, for radical 3. And so plugging that back in over here, we got x is equal to -6 plus or minus 4 rad 3 all over 6. The back of the book may simplify that answer even more. You don't have to do that. As long as you simplify the radical and the radical didn't go away still, there's really nothing more that you can do that I require anyway. Okay, but notice, you guys, that as I promised you, since the original problem was a degree 4 polynomial here because of the x to the 4th, we got 4 answers here, don't we? Remember, the plus or minus means that this is 2 different answers right here. So 1, 2, 3, and 4. All right. So that's what happens. All right, in these problems, you can find 4 zeros if you count imaginary numbers and you count multiplicity of zeros. Okay, like we saw in number 9. All right. Number 11. Okay, number 11, we're going to look at, once again, just like in number 10, since we're finding zeros here, we first of all want to set this equal to 0. So this is kind of a bigger problem, so I'm going to give myself some space over here. So I'm going to set this equal to 0. And then after I set it equal to 0, I'm going to, just like in the last problem, just like the directions tell me on the previous sheet, factor out the GCF. Once again, we do have one. It is equal to x once again. It won't always be equal to x, but it just so happens that it has been here in the last couple of problems. Okay, once we factor out the GCF, we got to take that leftover polynomial we got. And again, just like in the last problem, after you factor out the GCF, you have to take the leftover polynomial, and since they do not give you a 0 to try, like they did in the problems on the previous sheets here before this current sheet that we're on, and because we can't do the conjugate zeros theorem because there's not an imaginary number to start with, we need to do the rational zeros theorem, just like we've been doing on the previous couple of problems. So what we have here is we got to take the coefficient of the term that doesn't have a variable divided by the coefficient of the highest degree term. So we have 72 factors of 72. Let me zoom out so you can see all that. Factors of 72 divided by factors of 1. All right, let's see how that looks. Okay, it looks like we're going to have a lot of numbers there. And the truth is we will. But it doesn't mean it's going to take forever to find the answers here. Okay, so don't worry about that. So factors of 72, we have what? We have 1 and 72. 2 and 36. 3 and 24. 4 and 18. And I can see I'm running out of room here, okay? 6 and 12. 8 and 9. I'll squeeze that in up here. And that's divided by 1. But we need to say plus or minus for all of these here. Okay, plus or minus for all of these. Okay. So got lots of possibilities here. The good news out of all this is that, pardon me there, it's kind of small, but those all got pluses or minuses in front of it. When you divide by plus or minus 1, I'll clean up this mess here. Just like in the first problem at the top of the sheet, when you divide by plus or minus 1, it's just going to be equal to the numerator. All right, so, and I'll make it look a lot more clear here. We'll spread it out here. All right. So lots of things. As I promised you, I won't make it too big. All right. As far as the numbers that you can use in order to get down to linear and quadratic factors. All right. Doesn't mean you won't eventually have roots that are big sometimes, but you just won't need them to get down to where you need to get. All right, there are all the possibilities. Like I said, since you can usually get some of the smaller numbers to get you to where you need to go. Start out with checking the 1, and then checking the 2, and then checking the 3, and hopefully something will come along that you can will have a remainder of 0 here on the synthetic division, which means you can factor it. Okay. So again, to save time here, just let me tell you that 3. All right, normally you're going to have to test it out repeatedly until you find one that works, but I already know that 3 works. Okay, and on the test, when you take it, I will take that into consideration when I consider how much time you need to take the test. But also keep in mind, as I move back over here, sorry about that, 3 is what I'm going to test out, and I'm going to test it out on what? I'm going to test it out on, again, what's left over after you factor out the GCF. The GCF is a linear factor, x minus 0, so leave that alone and just deal with what you got left over. Try to break that down to smaller factors, and that's why we put that leftover bracket into the top of the synthetic bar, just like we usually do, all right, to continue to break it down. Let me do the synthetic division here. There we go. And so, what does this now factor down to be here? The x is still there, okay? The factors never go away after you pull them out. It's just that you're trying to take the one that's neither linear nor quadratic, and you're trying to break it down to smaller factors. But the x that is in front there is still there. So we got what? We've got x minus 3 for the first factor. The bottom of the synthetic division there is the other factor, x to the third minus 5x squared plus 14x and minus 24. So we're almost there. What do we got now, you guys? We got a linear factor, x minus 0. We got another linear factor, x minus 3. And then finally we have this factor that is neither linear nor quadratic because of the x to the third term. So we got a little bit more work to do. All right, let's go ahead and try. As it turns out, you guys, again, to save time here, 3 works again. Remember, sometimes the same number works more than once. That's why we were talking about multiplicity earlier. So again, just do it based off of the one that you're still trying to factor. The linear factors are already out of the way. Just build off of what you're still trying to break down. Put what you're still trying to break down into the synthetic, or underneath the synthetic bar rather, and let's see what we get there. Okay. And you can see here that it gives me a remainder of 0 again. Okay, that's your friend in this section, a remainder of 0, especially in these problems. So again, the first 2 factors are already in place. Okay, we don't want to change those. Those are linear. That's what we want. And then the big bracket right here that we were trying to break down here by putting it into the top of the synthetic bar, that becomes what? It becomes x minus 3. Okay, so we got 2x minus 3s here. That just means that the 0 equal to 3 as a multiplicity of 2. And it's got 2 factors. And then we got x squared minus 2x plus 8. X squared minus 2x plus 8. Okay. Now that we have broken it down to 3 linear factors and a quadratic, we can now, and not before that, but now that we have all linear or quadratic factors, set everything equal to 0. Okay. Okay. Let's see here. Let me, I don't want to do that. That looks weird. Let me make some more room here by moving some of these over. I want to fit this in so that you can see it all in one line here. There we go. There we go. All right. So let's solve these. We got x equal to 0. Moving over the 3, we get x equal to 3 2 different times right there. Remember, if a 0 pops up more than once here, when you set your different things equal to 0, don't write them out each time they pop up. Okay. And then this right here, believe it or not, you can't factor that. If it was minus 8, you could. So we need to do what? And again, I'll do it off to the side here just to do my work. We got to fall back on the quadratic formula right here since the factoring won't work. And so I'm going to do that off to the side here. Let me zoom back out. There we go. There we go. All right, and what is all this equal to? This is going to be 2 plus or minus, and then this right here, remember, you got to do the inside of the radical first. 4 minus 32. So that's 2 plus or minus the square root of negative 28. Remember, we're acknowledging imaginary answers here, so the fact that you have a square root of a negative number should not alarm you here. All right, that's still going to be part of your answer. How do I simplify square root of negative 28? That is equal to I times the square root of 28. I times the square root of 28. Simplifying the I. Okay, or simplifying the 28 rather, you get 4 and 7. And so this is going to be equal to I times 2 rad 7, which is equal to 2I rad 7. Okay. Now, bringing that back in, we now have what? We have x equal to 2 plus or minus the square root of 2I rad 7 all over 2. And yes, you could simplify that by factoring out the 2 and then canceling with the 2 down here. You'd have to factor first because there's more than one term up here. I don't care if you do that or not. It's not a bad idea to do it. You just don't have to. All right, so you can leave it like that. It's your choice if you want to do that. But notice here again that you have a total of what? You have a total of 5 answers if you include the 3 twice here since it popped up twice. Okay, 1, 2, 3, and then the plus or minus means 2 more for a total of 5. All right, and again, this is not a surprise because the highest degree term in the function was 5. All right. As we talked about, that should tell us that there's 5 answers if you include the imaginary numbers and the fact that 3 counts twice here. All right, one more problem here. Number 12. Number 12 is actually a lot simpler. We're not going to need the rational zeros theorem this time. You'll see why here. Again, you set this equal to 0. And so let me do that. And after I set it equal to 0, I factor out the GCF if it's not equal to 1. And as it turns out, it's equal to x squared. And this is what we get right here. Check this out, you guys. We actually have two quadratic factors here. First of all, when you got a term times a bracket, that's your two factors right there, the term and the bracket. But both of them are quadratic because both of them have x squared as their highest degree term. So we're actually done as far as having a factor. We can set both of these things equal to 0 right now. Because, like I said, you just need to get down to linear or quadratic factors here. All right. With rare exception, like we talked about earlier, all right? Normally, getting down to linear and quadratic factors will get the job done. All right, we had that exception earlier with the imaginary coefficients in the quadratic factor. But normally, like I said, this is all you need is linear and quadratic factors when you're trying to find zeros. But by the way, we haven't seen this before. It's so small, but whenever you got a term, any term that has a variable in it, and it's equal to 0, and I'm only talking about 0 here. Single term on one side, 0 on the other, okay, and it has a variable in that single term, okay, the answer automatically is 0. There's no other way that any other number could make this true, okay, only 2 could make that, only 0 could make that true when you have a normal monomial term here where you got a coefficient and then a variable and a whole number exponent, that kind of stuff, all right, only 0 would make that happen. And then here, this is the Berry method, all right? So things are materializing real nice here, all right? 2 times 10 is 20. What two factors of 20 are going to give us a sum of -9? That would be -4 and -5. So we got 2x minus 4 and 2x minus 5. We still got to do the last step of the Berry method. Factoring out the GCF out of that first bracket, we got x minus 2. All right. And then factoring out, there's no GCF to factor out of that second one. So this is it right here. We just now need to set those two brackets equal to 0. As we do... Wrote a little bit too fast there. Set those two factors equal to 0. As we do anytime we use the factoring method on a quadratic formula, or not quadratic formula, on a quadratic equation. All right. Solving these, I get x equal to 2, and then on the other one, if I move over the 5 and divide out the 2 like I normally would, in a linear equation like that, which is not what it's now become. This little equation here is linear. I now have x equal to 5/2. So I have a total of 3 answers. And now, let me clarify something here. I know you're probably thinking, wait a second, I thought it was supposed to be 4 answers. Okay, it is. It's just that, remember, x squared, you don't have to write this down, but x squared actually is the same thing as this. Again, don't have to write this down, but just to clarify that whole thing about how many answers we have. X squared is the same thing as x times x, which is the same thing as x minus 0 times x minus 0. So if you wrote it down as linear factors, all right, you would have, you essentially would have this right here. You'd have x minus 2 and 2x minus 5 if you include these two factors from the other quadratic factor here. All right, let me get that on the screen there. So these two factors come from the big red one. These two factors with the zeros come from the little red one. And so you have a total of 4 factors. If you set all 4 of those equal to 0, you would get 0 as an answer, 0 as an answer, 2, and then 5/2. All right, so theoretically, because of the x squared being the same thing as x minus 0 times x minus 0, the x equal to 0 actually occurs twice. If you don't remember to write down x equal to 0 twice, and I didn't even do it here, that's okay. All right, that's not normally what happens there when you get x squared equal to 0. Just, you know what though, just to be, and again, don't worry if you don't do this, I won't mark you down, but I will write that down twice because of this situation over here, okay? Just to be completely consistent with what we've been talking about on the last few problems, all right? But if you'd forget to do that, don't worry about it. All right, so that concludes section 3.3, maybe the longest section in the whole book, if I'm not mistaken. And once again, as always, you guys, please don't hesitate to contact me with any questions or concerns. Have a good day.